Hello. I think it's pretty loud already. Is it too loud? No? It's good? Okay. Let's make this bigger. How come this is so small today? Oh, I know why. Okay. Let's see. Homework 4 due tonight. Write-up. Why is the write-up for Lab 4 is still open, but it will close tonight. Absolutely. So if you haven't got that in, or if you want to make a last-minute change, do it before tonight. Let's see. Homework 5 will be up tomorrow. Okay, so today I left open to answer more questions about Lab 6 if there are any, but we can put it off till Friday too. Yes?
So for when the slug is hovering, it flashes on and off. How are we supposed to do that without a quarter second signal? Are we expected to make our own alternating signal?
Well, let's see. I think there's something here about that. Number 8, there is no QSEC signal. Don't try to put QSEC clocks into your design because, of course, it's not going to be compatible with the clock module for the FPGA that you need for the VGA. So instead, it suggests that you count frames because you're going to have a frame signal anyway. The frame signal goes high once for every frame, and there are about 60 frames per second. So the frame signal is 1/60th of a second. You want the quarter second. If you want a signal that's about a second, you can count up to 64. That's close enough. We're not going to notice a difference between 64 and 60. I say 64 is convenient because it happens to be a particular bit of your counter, right? If you want to make it 60, you can make it 60. Any other questions? Everybody's figured out everything, right? You all going to be done on Thursday? No? Okay, all right, we'll talk about something else then. All right. I thought I would, it's not on the schedule, but since we seem to be ahead, I thought I would talk about division. All right. So we did the multiplier last week. But what about division? All right. So again, I think this time we'll go back to 4th grade. Or maybe they're more accelerated these days than when I was in school. But does this seem familiar to you? You were asked to divide, and what you did first was say, okay, let's just look at those first 2 digits because 12 is 2 digits, and ask ourselves, how many times can we fit 12 into 15? Once. Okay. And so then we took it away. And that left 39. And then when we asked ourselves, oh, darn it, how many times does 12 go into 39? Don't look, no. And the answer is 3. And so we subtracted 36. And then that was it. And we had a remainder of 3. Right? Okay. So that's how you would work it out. Now, you were doing some things that you probably didn't realize. And that is that you were skipping the first step, which is asking how many times does 12 go into 1? Because you thought that was a silly question and no reason to even bother with that. We'll just go directly to 15, right? But if you were doing this in general for 3-digit numbers, if you had to tell somebody, here are the steps you do, regardless of any of the numbers, you would say, okay, first ask yourself how many times does a divisor go into 1? And you might think, well, that never happens. But yes, it does happen. If you were dividing by 1, right, 1 does go into 1, and your first digit in the answer would be 1. Dividing by 1 would actually give you the result 159, hopefully. Okay, so the first thing was to align this number with the most significant digit, and you had to extend this so that it has as many digits as the divisor. Now here we're doing it assuming both numbers are 3 digits. So 12, even though only 2 digits are necessary, we would be, in a mechanical process, we would be dealing with 3 digits. Okay, so you did this unnecessary step here, and then the rest pretty much follows what you did here. Okay, and probably what they didn't tell you in grade school is that the different components or numbers of this process have special names. The thing you're dividing into is called the dividend. The thing you're dividing by is the divisor, that you might have heard. Quotient is the number of times the divisor fits into the dividend, the maximum number of times. And then, of course, we have a remainder. And the quotient and the remainder are unique numbers that satisfy the following constraints. The quotient times the divisor plus the remainder add up to the dividend, and the remainder is always less than the divisor. And there are, assuming these are all positive or non-negative integers, there is no other choice. These are unique. How many of you prove that in discrete math? Okay, yeah, all right. Okay, so here's a more tabular method of what's going on, right? We have a dividend. We are attempting to subtract the divisor, except this time we realize only goes in 0 times. And then we shift the divisor over. Now we realize it fits 1 time. And then we subtract. And this time we realize it fits 3 times, and we subtract again, and we're done. 3 steps, 1 for each digit. So now we're going to do the same thing in binary. The same exact numbers. Okay, this is 12. We are assuming 8 bits. Okay, obviously we don't need 8 bits for 12, but we're doing this in general for all 8-bit integers. Okay, so how many times does 12 go into this? None. Okay, shift it over. How many times does it fit? None. Still doesn't fit. Still doesn't fit because this is 12, but this is 9, right? Aha, it fit. Okay, so if we look at these first 5 digits, this is 19 and this is 12. 19 minus 12 gives us 7, and then we carry down these 3 bits. Okay, Keep going. It fits again. And it fits again. No, it didn't fit here. It fit again. And at the end, we end up with a remainder of 3. And these are the digits of our quotient produced one at a time. Okay. So this is the method we're going to use to create an 8 by 8 divider. There's a few little subtleties here. So notice that these numbers didn't quite line up, right? And so what was really happening is we were filling them with zeros. Okay, so we had our dividend up here, A, and we extended it with zeros here. Of course, likewise, we took our remainder and we put zeros to the right. And when we did this, okay, so these were 8 by 8, we got 15-bit numbers. Okay, so we were doing a 15-bit subtraction all the way down to the end, getting 1 bit of the quotient in each step. There's one more subtle thing here, is when we do subtraction, we need to know that whether the result is going to be positive or negative. And since we're assuming these are all non-negative integers, we'd like to be able to tell quickly whether or not subtraction leads to a non-negative number, right? And if we use 2's complement, we can tell just by looking at the leading digit to see if the result of the subtraction is negative or not. Yes? They're not terribly different. And since you're going to have to probably do the subtraction anyway, you might as well try it. Okay. All right. So in order to tell easily whether the result is positive or negative, we extend these by 1 more bit so that in 2's complement, these are positive numbers. And if we ever get a 1 here, we know the subtraction ended up in a negative number. Okay. And so then we would actually be doing a 16-bit subtraction. Okay. All right. So that's the method we're going to use to do division. We're going to repeatedly subtract the divisor, starting by aligning it with the most significant bit of the dividend extended by 8 bits. And then we're going to shift D at each stage. Okay. So this is the symbol for our sequential divider. I'm using n here, right? In the example, n was 8. So we have our 2 arguments, the dividend, the divisor. We have a go signal. This will output 2 n-bit integers, the quotient, and the remainder. And also it'll tell us when these values are actually valid and when the divider is not busy. Okay. So this shows the operation of the divider. Okay, so initially when you start it up, it says it's ready. And we don't know what Q and R. There's no, since you just woke up, the quotient and remainder could be anything. There wasn't any previous operation. And on the first clock edge, where go is high, whatever values on A and D are present will be used to start a division. And they only need to be valid on this clock edge. Afterwards, they can be anything they want to be. until the next go signal. Then they matter again. Okay, so we got a go signal. Immediately after the clock edge where go is high, you'll see ready goes low, because now the divider's busy, and it's going to churn. And I didn't specify how many clock cycles here because I needed this to fit on one slide. So there's a bunch of clock cycles in here, and then eventually you see ready go high. And when ready is high, that means that the quotient and the remainder are valid. And they will remain valid. They'll stay put until the next go. Okay, now what they are in between here, they're used for calculations, so they're not correct. And they shouldn't be actually read until you get the ready signal. Okay, so here we go. All right, so here's the next calculation. Again, A and D have to be valid at the next go. The other thing is that the go signal could be anything. Doesn't matter what the go signal is while the divider is busy. It's going to ignore the go signal. Go signal won't do anything until the divider is ready, and then once the divider is ready, don't start it unless you want it to divide. Okay, all right. So what do we need to do this? All right, so let's look at what's going on here. So this is the operation that we're doing, right? So I'm going to need a subtractor. Okay, that's easy. There's my subtractor. Okay. And we said it was going to do subtraction of 2n bits. Okay. What is it subtracting? Okay. The original divisor? What?
Well,
The offset?
I guess as a correction, like the divisor is put into a shift register.
Oh, okay. So we're going to want to shift the divisor. Okay. Which direction?
Right?
Right. Okay. All right. So we want a shift register. We want, okay, obviously this needs a clock. We need it to shift right. What is it going to shift in? You know what? 0, right? It's going to shift in 0. I mean, I could spend 8 cycles shifting in the divisor, but instead I'm going to provide a load. Okay. So we're going to load, let's see, we need to load D. How many bits in this shift register? Oops. Two N? Okay. 2n. Okay, but D's only n bits. Okay, I'm going to pad it with zeros. Which side? Okay. But hang on. What is that first one I want to subtract? It had one, actually, I'm going to cheat and have 1 0 on the left side. Save myself a shift, right? Because I got to slide that divisor over so it lines up with the first bit of the, so I'm going to put 1 0 on that side and n minus 1 on there. Okay, so I have 1 0, I have 8 bits of D, and then I have 7 bits of 7 zeros. Okay, that's easy. What about the other one? What am I subtracting from? Yes?
It's kind of the dividend and the remainder.
Okay. If I do it right.
With the dividend,
Okay.
just a register. And every time you both do a subtraction, you can load that back into that same.
Okay. So initially it'll be the dividend, right? And then if I end up being able to subtract, I'm going to load the remainder back in. Okay. All right. So this is not shifting. It's just a register. It can load then. That's about all it can do. And it sounded like there were two things that I wanted to load, right? I want to be able to either load A or, whoops, that was bad planning on my part. Let's not put A there. Or the remainder. Right? If I manage to subtract this from A, then I want to put this back into. So in fact, this register is basically holding the remainder. And initially we started with A, with pad extended with zeros. Okay, so this is A is n, but I'm going to add n zeros here. So I'm going to call this 1. and call this 0. And let's see, I have a selector here. All right, I'll put it on this side. Okay. So I need some control, right? If I want to load A, then I'm going to make this selector high, and it's going to load A. But I might also want to load it at another time. So, okay. Let's make an OR gate. And we should either load this register if we want to load A, or if we want to load the remainder. Does this make sense? Yes. Okay. Where's the answer? Where's Q? Yes. This is the remainder, right? We covered the remainder, but hey, where's Q? That's the whole point of this, is to get Q. I need another register. Okay, so basically, I'm generating the bits of Q one at a time, each step, right? If I'm able to subtract, then that bit is 1, and if I'm not able to subtract, that bit is 0. So I'm going to get these bits one by one. How do I capture and store these bits? If you had a stream coming in, one bit at a time, and you wanted to store the last 8, what would you do? What? I hear another shift register. Okay. So we need another shift register. And this one is going to hold the n bits of Q. Okay. Okay, all right. So these bits are coming one by one. Is it most significant or least significant first? So this first bit up here that I'm going to get, is that going to be the most significant bit of Q or the least significant? You have a 50-50 chance here. Most significant.
Yes,
Most significant. Okay, so I'm getting these most significant first, and I want the most significant to end up on the left. So which way should I shift? Okay, shift right. Okay, so we'll have a shift right. I'll call this SQ. All right. And, well, what am I shifting in? I'm shifting in, what am I shifting in? Yeah.
the most significant bit of the subtractor, if it's into complement.
Okay, so the most significant bit tells us whether or not the result of the subtraction was negative or not, right? If it's negative, it's the complement, right? So if the most significant is 0, that means that the result is not negative. And if the most significant is 1, then the result was negative. So we can pull out all right, I'll just make this easy. I'll make an output called greater than or equal to. And inside, this is the complement of the most significant bit of the result. Okay, so we're shifting that in. Okay. Sounds like a plan. Okay, how many steps am I going to do? Because I have to tell the world when the result is ready, and I don't want to. I need to stop at 8, because if I don't stop at 8, now I'm shifting out the part of the result. No? How do I know when I'm done? It's 3:45. No. Yes. N times. How do I know it's been n times? Okay, so we could add a counter loaded with n and decrement or count up to n. Okay, but here's a trick we can use. That's since we have this shift register, what we can do is add a reset. So this is a reset Q. And this will initialize to, so we used n. So this would be n quote B1. So what it does is it initializes to all zeros with a 1. And basically when the 1 comes out, you're about to do the last step. Okay, because you wouldn't need to initialize this if you were doing n steps, because you'd be just shifting out bits you don't want anymore and don't care what's in there. But basically by initializing this, we can then use it as a counter. It's a ring counter, I guess, if you like, except it's not coming back. It's shifting that one in. So when this one comes out, the other end, we're done. Okay. All right, so that's what we're going to do. And we're going to get this. Okay, so this is essentially what we have on our paper. Here's the shift register for D that shifts right. Here's the register for A, which, or the remainder, and we can either load A into it or the result of the subtraction. We only care about the outputs, only the lower end bits of the remainder. We're guaranteed not to have any non-zero bits in the upper. The remainder is always going to be less than n bits. Less than or equal n bits, right? And here's our shift register for Q. It shifts left, and GE is what we shift in. Okay, so we need this control here. And this control looks very much like the multiplier. It only needs two states. Basically, we wait for the go. When we get the go, we initialize everything. And then we keep shifting and subtracting. When we notice that it's the last subtraction, and we'll know that by the output of the shift register, the most significant bit of the shift register, then we go back to chill. And we only load the remainder when GE is high. So remember, we need to actually do the subtraction if the dividend or if the remainder is greater than or equal to the divisor we're trying. Okay, so this is pretty simple, and we can make our table again. Does this look familiar? Except now we have 4 different cases for TEP sub. Right? Basically, we need to know, based on last, that determines whether we stay in test sub or go to chill. And then based on GE, that determines whether we load the remainder or we don't load the remainder. Okay. Because we need Q and the remainder to hold until the next go signal, we need SQ and RQ to be fixed. They can't just be question marks. We need RQ and SQ to be 0 while we're waiting for the next go. But LA, LD, those could be anything. I guess I could have put a question. No, I can't put that. Okay. All right. So in fact, we only need 2 signals for 4 signals. The 2 shifters shift together, so we only need 1 shift signal, and then the 3 signals that initialize the registers, those can all be the same. Okay, and here's your next state and output equations. All right. Okay, so this is how you might build a divider. There are much more sophisticated algorithms for division than this, and there's less sophisticated ones too. There's one where you use a counter and just keep subtracting the divisor until you can't anymore. And you use your counter counts up, and that's your answer. Okay. All right, so I'm calling this the shifting D design because we were shifting D to align it with A, right? A was fixed, and we're sliding D across. And this is what you do when you did long division. Okay. It will take us exactly n+1 clock cycles. So there's that one transition to get to the test sub, and then you're going to do 8 shifts or n shifts. So exactly n plus 1 clock cycles, and you have your answer. One of the downsides of this particular approach is that you have a really big adder. That subtractor has a 2n bit. Now, 8 bits, fine. But if it's 64, you start to care. All right. So there's a trade-off here. Although it has the minimum number of clock cycles, unless we go combinational, in which case it would be less than 1 clock cycle, you have a fairly large delay because of that adder in there. So can we improve things? Well, if instead we were shifting A, so let's go back to this slide for a second. So when we're doing this subtraction, it's only where D is that I'm interested in the subtraction. So if I were to start to shift A, I wouldn't care what these 7 bits of A are. They're not relevant. I'm not subtracting from them. Or I'm subtracting 0 from them, which has no effect. And so I only actually need to subtract where the divisor was. And that's only n bits. So I could get away with an n-bit adder instead of a 2n bit adder. But there's a downside to this. Nothing's perfect. And if I'm going to fix D and slide A, it might require 2 cycles for a step, because now I need to shift the remainder. And if I need to load the remainder and shift it, I can't do that simultaneously. Okay, or I need some complex logic to do it, in which case I'm slowing things down again. Okay, so there are trade-offs here on how you do this. The length, the amount of time, the amount of work you do in a cycle versus the number of cycles. Okay, sort of like college. The number of classes you take versus the amount of work you do per class. Right? Okay. All right, so let's go back here. All right, so this is what shifting A looks like. D is the same here. We're always subtracting D, but we're sliding A over. And if we don't need to subtract, so in the first 4 bits, we didn't subtract because the divisor was bigger. But eventually when we get to this step, we do the subtraction, then I need to load the remainder, and then I can subtract. Load the remainder and shift it, and then I can subtract, right? And so I have 2 steps here where it took me 2 cycles instead of just 1. Okay. And this is what this design looks like. Very similar. Again, we have our shift register for Q, exactly the same. We have a subtractor, except now it's only n plus 1 bits. Now, we're going to do the same trick of adding a 0 so that our 2 numbers are positive in 2's complement, or non-negative in 2's complements, and we can... Okay. Our D doesn't shift, so it just gets loaded into a register, and it's held there. Here's the remainder. Now, what's going on here is we've broken up this 2n-bit remainder, or 2n plus 1 bit remainder, by loading A into the lower bits, and then we have to shift the most significant bit in A into the least significant bit here, right? So right? Each time a new bit of A comes into range, right? We're slowly shifting A. So this is the part that gets subtracted from, and this part is just sitting, waiting to be part of the action. Okay. All right, so this is the part. And then, of course, if we actually do the subtraction, we're going to load this part again and then shift a bit in. Okay. All right. And here's our state machine now. Unfortunately, we need 4 states. So we have a setup here. Now, I made things a little bit simpler for myself. And in that, I made a setup state. So basically, we would load A and load D and reset Q, and then we would shift the first bit of A into the remainder. You can certainly make your shift registers inputs more complicated so that you directly can go to test instead of having this extra step. Okay, but that's not the biggest problem. Okay, once you're in setup, then you have this 2-state cycle here. If you're not going to subtract, you don't need to go to sub. You can just stay here and shift. But if you do need to subtract, then you need to actually load the remainder, go to sub, and then come back and shift. Okay. All right. So these are the 2 cycles that you need when you have to subtract and shift. Otherwise, you can just keep shifting while you're in test. Okay, here's our state table. Here's the states. I think I forgot to shift A here. I think we need a shift A here. Okay. Any questions on this? No. So often when you're designing, you're going to have this trade-off between the complexity of what you do in a cycle versus the number of cycles. Right? And those of you who've taken 120 know this. I've seen this trade-off many, many times. Yeah?
In general, would you say the first setup we have is better?
Again, it depends. What is your target clock? Generally, your divider wants to work with something else. If it's not the bottleneck, then by all means, you use the first one. It's simpler, right? But if you need a very fast clock, then probably you don't want that 2n bit adder. Or you want to spend some time making your addition faster, which you can also do, but it's going to cost you an area. I'm sure you've heard there's no free lunch here. It's always if you go and take the theory classes, that's what it's about. There's always these certain complexity bounds that you can't escape. But which particular constraint's most important to you depends on what you're doing. Okay. All right. So those are our signals. We combined some of our outputs together, so we only had 6 outputs. SH. there's our logic, our state machine logic. Okay. Shall I do one more? Or you want to wait till Friday? I do have 20 minutes. Go for it? Okay. What?
I said yeah.
Yes, okay.
Go for it.
Clara said yes.
I'm going with the most to lose from class going slightly longer because I've got the overlapping lab.
Oh, okay.
And I'm for it.
All right. So we built a multiplier, we built a divider, and now we're going to build something that's not just going to use gates, but it's going to use another sequential component. Okay. So we want to build a processor which is going to compute the factorial of n. So it's going to take an input n, a go signal. It's going to compute n factorial, and that's going to be the output. Now, of course, this is rather limited in the size of n's that it can consider because factorial is exponential, worse than exponential, in fact. But anyway, this works with our multiplier. Okay, so how many of you know anybody not know what factorial n factorial is? All right, let's put it this way. Who knows what n factorial is? Is everybody raising their hand? You're going to make me explain what n factorial is.
It would be funny.
You all know, okay. All right. One thing that you may not remember is that 0 factorial is essentially 1, is in fact 1. You might be wondering why. Because the definition says multiply all the numbers between 1 and n, and 0 isn't there. So you never multiply 0. And when you multiply no numbers, you get 1. Just like when you add no numbers, you get 0. If you have an operation with the identity element and you don't do any operations, then you get the identity for that operation. Okay. I'll let you ponder that.
It occurred to me that the basic math operations like multiplying and adding had default values.
Uh-huh, they do. That's so you can always break them down and they have no effect, right? Okay. Okay, I'm not going to take that personally.
The fact that it is unnerving to me that the default number is 1.
Okay. All right, so how are we going to do this? Well, basically we need to count down from n, and we need to multiply all the values until we get to 1. Okay, so to do that, we're going to have a counter. We're going to load n in there, and we're just going to decrement. Right, so just like your 15-bit counter, we could use that. But then we're going to need a multiplier. Right, and we're going to do these multiplications one at a time. So we're going to need to put it in a loop and have an accumulator here. So we're going to start with the value 1 in this register, because if I start with 0 and multiply, I'm only ever going to get 0. Right, so we're going to start with 1 here, and then we're going to multiply each value with the previous values that we've already combined, right? So basically our recurrence is that n factorial is n times n minus 1 factorial. Except instead of counting up from 1, we're going to count down from n. Okay, so that's pretty much that's fairly simple. We need a control. The control needs to know when we've reached 0. We certainly don't want to multiply 0 because that will wipe out the result. Not a good idea. We need to load this register, and we need to know when the multiplier is ready. Remember, we built that multiplier, and it can take anywhere from n to 1 cycle to produce a result. But it has this ready output, and this ready output will, what you're calling multiplier done, is going to go into our control, and so our control is going to know when it can load the register with the result. Okay, so this is fairly simple. So when we start out, what should we do? Right, this is for the control, right? The control has 3 inputs. It has go, 0, which tells us when the counters reach 0, and MD, which tells us when the multiplier is done or ready. Go will advance, so not go will keep you there, right? Okay. So we gotta go. Is there anything we need to do? Any housekeeping we need to do before? Yes.
Letting the world know you started an operation.
Okay, so we're changing states, so our ready will no longer be high. Okay, so ready is going to be low in all these other states. It's only high and chill. Anything else we need to do? Yeah.
We need a load value.
Okay. Which is where? Okay, load the counter. Okay, and also I need to initialize this register to 1. Right? I don't want it to be 0. My first multiplication is going to be 1 with the value I've loaded in this counter. Okay? So I'm going to load n into the counter, load a 1 into this register here. And then I'm going to start the check. Okay, I'm going to check if I'm done. Okay, interesting. Can I be done right away? What?
If they give 1 or 0, then you're just done.
That's true. If the input n was 0, I'm done, and I have the right answer here because I loaded a 1 there. Okay, so if in fact the counter is at 0, I have the answer. 0 factorial is 1, and I'm done. I could check also for 1, yes, but I'm lazy. So, okay, so if it's not 0, what should I do? Yes.
Start up the multiplier.
Okay, let's start up the multiplier. Okay, so I have the value n sitting here. I have a 1 here, so I'm going to multiply n with 1. Okay. I'm also going to make this count down because I'm done with n. I want to advance it to the next number. Okay, and then I'm going to go to a state where I'm multiplying. And what am I going to do in this state? Read magazines. No. Okay, I'm waiting for that multiplier to be ready. I don't know how many cycles it'll be. If it was 1, it'd actually be very short. We know it won't be 0 because we took care of that. Okay. All right, and if it is done, what should I do?
Load the register.
Okay, then I want to load the register, and where should I go? Back to check. Okay. So I decremented this, right? Okay, so when it's done, now I kind of saved myself a cycle here and said, hey, and if it's 0, just go all the way back. Okay. Why didn't I load F anyway? I could have loaded F. Yeah?
If it is currently 0, that means you just multiplied 1.
By 1, and it didn't change, right? Okay. Yeah, so either way, you can load F or not load F. The last multiplication was useless because you multiplied by 1. Okay. All right. So that, oh, I did do it. Oh, never mind. Okay. I didn't need to do it. All right, so that's the entire design of Factorial. All right, some key points here.